Okay, I'll see her pop up in here and then I'll just put allow. Okay, so here we go. This is the start to some brand new stuff. And you're gonna see that hopefully this material, it won't, we don't have much left. I think if we go pretty average speed, by spring break, we'll be done, hopefully. All right, area under the curve. I think you guys already have some experience, I think, because you guys have been doing, all right, let's talk about the experience that we have. So let's say you're in a train and this train goes 50 miles an hour. So I'm gonna write velocity and time. And it's going in miles per hour, mph, and I'm saying 50. And this train travels for 4 hours. How much distance have I covered? Yeah, how'd you do that? How'd you do that so fast? Yeah, 50 miles per hour times 4 hours gives you 200, right? So notice this area under this curve is that 200, 50 times 4. Do you guys notice that? All right, so the area under the curve of a velocity time graph gives you distance covered. Cool. All right, so now let's say I have a variable velocity. The question I want to ask is the area under this curve still distance covered? If this is still velocity in miles per hour, but it's variable, it's going up and down, and that's time. Would it still be distance covered? Yeah, it's actually displacement, but we'll talk about direction when we get there. Yeah, it would still be the distance covered. Does that make sense? Now, how are we gonna find area under irregular curves? Because this is not like a regular curve, it's an irregular. It has, so that's where you need calculus, guys. But don't worry, we're gonna start really simple. We're gonna start with these three: LRAM, RRAM, MRAM. They are Raman sums. You don't have to worry about this guy named Raymond at the moment. It's a Raman sum. I'm not sure if he discovered it, but he definitely put the technique in there. The L, let me tell you what each letter stands for. LRAM. The L stands for left. The R stands for rectangular. The A stands for approximation. And the M stands for method. Left, rectangular, approximation, method. What do you think the R stands for? Right. What do you think the M stands for? Middle or mid. And we're all going to be doing examples of, I can never spell it correctly, Raman sums. And we'll talk about this Raman guy. All right, example 1. A particle starts at x equals 5, so I'm at position 5, and moves along the x-axis with velocity. So this explains how my velocity is going to, this is going to tell me my velocity time curve, right? For a time t greater than or equal to 0. Using n equals 6, so this means to use 6 rectangles. Subintervals of equal width, approximate the total distance traveled between t equals 0 and t equals 3. Use LRAM, MRAM, RRAM. Once you find the distance traveled, where is the particle at t equals 3? Man, we got a lot to say here. Now, notice I put a lot of white space. That white and then the next white. That's because we're going to be taking up all that time. So before I relax, guys. V of t equals t squared. That graph for t greater than 0 looks like this. And I'm going to exaggerate it. Cool? So let's draw a big one right here. Draw it big. And oh, if you have colored pencils, this will be a good place. From 0 to 3. Okay, so I'm going to say here's 3. Now each rectangle is going to be equal width, correct? So how many rectangles do I have again? So if I want to know the equal width, your delta x, I'm going to go between, let's see, 0 and 3. So I'm going to go 3/6. So my delta x is going to be a half. Yeah. See this top right here, that 3? That 3 is this, from 0 to 3, right? And then I need how many rectangles? 6 of them. So 3 divided by 6 is half. So each rectangle is going to have a width of how much? Half. Does that make sense, guys? What's up, Jarilla?
So above is t equals 3, and then below it is that.
Really, that 3 is 3 minus 0. Whatever the interval is, I'm between 0 and 3. So if they were to tell you between t equals 1 and t equals 4, then you were right, 4 minus 1. You know what I mean? Like, yeah, and then divided by whatever rectangles. So you can feel like, so you can see what the delta x is going to be. Okay, so my first rectangle, I'm doing LRAM. So I'm going to do LRAM in blue. So if you have, you don't have to do it in blue. You can choose whatever your favorite color is. Choose your favorite color, whatever color you want. We're going to do this 3 different ways with 3 different colors. So my first rectangle, before I do anything, guys, I want to put my grid here. Let's see, if that's 3, I'm going to say 1, 2. I'm going to say this is 1, and I'm going to say that looks like 2. And I feel like I have an evenly spaced, for the most part, grid. So try to make it evenly spaced. All right. LRAM. It stands for left rectangular approximation method. I have 6 rectangles. Since it says L, remember each rectangle is a width of half. Since it says L, I'm going to start with the leftmost point on that curve. Leftmost point on the curve, 0. And then my first rectangle is between 0 and a half. So here's my first rectangle. You have no rectangle. It's right on the x-axis. And it actually doesn't go all the way to 1. It goes all the way to what? Half. So there it is. That's my first one. My second rectangle, go to half, go up on the curve, put a point, make it go down, and then go horizontally from that point on the curve all the way to 1. And there's my second rectangle right there. Does everyone see how I did it? Remember, you're starting at the leftmost point on the curve. So go to 1, put a point on the curve, go straight down. Boop. Now go back to your curve and go horizontally until you get to 1.5. Go to 1.5, go to the curve, point, straight down, and go all the way to 2 horizontal, and then straight down. Go to 2, right on the curve, put a point. These are all LRAMs. And then finally go to 2.5, point on the curve. Oh no, I'm done. Well, with the rectangle stuff. Doing all right? Oh, cool. Oh, there's another. Oh yeah. I got. Oh, no problem. Thank you. Sorry about that. And there it is, guys. You just did your first LRAM. Now, what's the point of all this? We're finding the area under this curve, but we're approximating it with rectangles. Now, before we continue, you can see we didn't do a good job of getting the actual area. The more rectangles we put, the better the approximation. Is this going to be an over or under or perfect? It's going to be an under approximation because we're below the curve, every rectangle. That makes sense? All right, so how do we, let's add them up. So how do we get our rectangle? Area of a rectangle is just length times width. So length is, well, half for all of them, right? Or I guess you can call this the width. This is your width here. And then the height is just going to be your f of x, right? So remember that the curve is t squared. Do you guys remember that? I'll write it here. F of t, I guess they wrote it in terms of, yeah, v of t, f of x. That doesn't matter, guys. Your velocity, f of x is x squared or t squared. It doesn't matter. So here we go. 1/2, that's the width, and then the height, 0. That's my first rectangle. Plus, look, because it's right on the x-axis. You guys see that? The next one, 1/2 times, what is that height? Was dictated by the curve t squared. This coordinate was a half right there. So you're going to write 1/2 squared. Have I confused anyone? You can write it as 0.5 if you want. Yes, the height, I got it from this curve, the red one, right? So this is my x coordinate or t. And if I want to know the height of that curve, this curve is v of t equals t squared. So I plug in my t value and I square it, and that's how I get the height. Cool. Plus, I'm still doing my half here. That first half is the width, the delta x. The height. What's the height of the third rectangle here? 1. I know that I'm putting a square there. It's just to be consistent with my squares. Plus 1/2 parenthesis 1 point. I'm going to put 1.5. Sorry that I'm putting fractions and decimals all over the place. Squared. Do you guys see where I got that? Plus 1/2 parenthesis 2 squared plus 1/2 parenthesis 2.5 squared. That's your last one. You should see 6. 1, 2, 3, 4, 5, 6. Oh, because at 3 I don't have another rectangle. Like because they told me to do 6 rectangles of equal width. So I have 6 of them. Well, technically 5, but there's 6. The first rectangle just has an area of 0. Because we're doing left rectangular. So between 2.5 and 3, I have to use the leftmost point. So I have to use a point at 2.5. I can't use a point at 3 because then, you know what I mean? Because I have to go left to right. Are we okay, guys? How do we feel? All right, tell me what all that is. I don't know what that is. Let me get my calculator. The first one is 0 plus, I guess you can factor out the halves, right? You can factor out a half and then parentheses go 0 squared plus 0.5 squared plus 1 squared plus 1.5 squared. Oh. Yeah, you need your calculators, guys. Practice with them. Plus 2 squared. Someone do it this way and someone do it like the way that we did in the paper. And see if we all get the same answer. I got 6.875. Okay. Did someone just do it like this? And you got the same? Perfect. So this area, we got 6.8. Charlie forgot it. 6.875. 6.875. And it doesn't have units because we have t squared, but you can just put units for now. Like literal word units. That's the area. Well, it's the approximate distance covered between 1 and 3. 6.875 units. Yeah, we're still gonna do it 2 more times. It is. No, because it would have been like miles per hour times hours. It would have been miles. But yeah, I guess if you're being technical, yeah, you could say square units. Are we okay so far, guys? Okay, let's do it again. But this time, I don't want to do MRAM yet because I want to do MRAM last. So let's do RRAM. So I'm going to exaggerate a grid. Oh yeah, you can, let's do a different grid. You can also do it on the same one if you want to compare. Maybe in a little bit we'll do them all, but I'm going to do a different grid. Take like half the paper. And just exaggerate it. 3, 1, 2, 2, 2, 2. I think I did an okay job there. And we said that we were gonna do which one? Oh, we already did it left with right, RRAM. So I'm gonna do mine in green now. I'm doing how many rectangles? 6. The first rectangle is between 0 and 0.5, but it's the rightmost, so I got to choose the rightmost point between 0 and 0.5. So the rightmost point between 0 and 0.5 is at, well, yeah, what 3 is the rightmost point, but between 0 and 0.5. 0.5, go to 0.5, down, and then left until you get to 0. So there's my first rectangle. Do you guys see it? Now go between 0.5 and 1. What's the rightmost point between 0.5 and 1? 1. So go to 1 on the curve, go down, and then horizontal line until you reach 0.5. There is my second rectangle. Yes, because I'm doing the right rectangular approximation method, I have to choose the rightmost point between an interval. Remember that we have 6 rectangles that they wanted me to do right there. So what did I do first? I found out how many, like what the width of each rectangle is. The width of each rectangle is a half. So I know that between 0 and 1, I have a rectangle, or 0 and 0.5, I have a rectangle. Between 0.5 and 1, I have a rectangle. Between 1 and 1.5, so here's my little hash mark for 1.5. Now I'm using the rightmost, right? So between 1 and 1.5, what's more to the right? 1.5. So I go to 1.5 and I put a point on the curve because that's what determines the height. And I just go straight down and I go horizontal until I get to this one right here. You see what I did? So there it is between 1 and 1.5. Continue it, 1.5 to 2, go to 2, straight down. 2.5. And now this one, check it out, Arispe. This one goes all the way to 3. This one you actually do have 6 rectangles for. What's up?
So this one would be an over.
Yep. This one is an over approximation because it's above the curve. Cool. Let's see. Oh, what's up? What's up, Geta?
So why does this one go all the way to 3, but the other one? Oh, never mind. Sorry.
It's all good. It's a good question. This one goes all the way to 3 because we're using the rightmost point from each interval. Remember that each rectangle has a width of half. So because we're using the rightmost point, between 2.5 and 3, we're using the 3. Did I answer your question there?
Yeah, I think I got it. Thank you.
All right, here we go. Let's calculate this area. 1/2 times, let's see, what do we use? 1/2 squared plus 1/2 times 1 squared plus 1/2 times 1.5 squared plus 1/2 times 2 squared plus 1/2 times 2.5 squared plus 1/2 times 3 squared. Someone do me a favor and take these numbers and type it into the calculator. If you're wondering, will College Board give me something like this? Yes, they've done it where you have to calculate 6 individual rectangles and you got to be very careful with your calculator. And we'll do some from College Board. I think the most I've ever seen is 12. But you have a calculator, guys, so, and I give you plenty of time. Let me know what number you guys get. It should be bigger than the last number. Yeah. Yep. Three squared, 9. 11.375. And this one, it's obvious that it's a what? An over approximation. We still okay, guys? All right, here we go. With the remaining half page, what do we got left? Middle? All right, let's do mid. So let's exaggerate that curve. I think we're okay there. All right, I'm gonna use black. We're using MRAM now. So between I'll wait, guys, I'll go slow. Between 0 and 0.5, what is the middle of between 0 and 0.5? 0.25. So you go to 0.25, put a point right there, and you're gonna go to the left, and you're gonna go to the right. So you should notice you have a little bit above and a little bit below the curve. Don't worry, we're gonna go slow. Here's my, yeah, I went to 0.25, guys. So look, check it out. There's this little hash mark is 0.5. There's my 1. What's the middle between 0.5 and 1? 0.75. So go to the middle, estimate it. You don't have to be perfect. 0.75. You go to the left. You go to the right. You should have a little above. You should have a little below. You should have a little above. You should have a little below. I'm gonna do it again. Don't, if you want to go ahead of me, go ahead, guys. No big deal. What's the middle between 1 and 1.5? Go to 1.25. You don't have to be perfect. To the left, to the right. You should see some above and some below the curve. I feel like a song. To the left, to the left, to the right. Okay, I'll stop. Between 1.5 and 2, what is that? So go to 1.75, to the left, and to the right. Between 2 and 2.5. 2.25 to the left, to the right. And then finally, between 2.5 and 3. 2.75 to the left and to the right.
Why do you put the line on the half line and not on the middle line?
Because they told me that they wanted 6 rectangles. So no matter what, that rectangle has to be a width of half,
Oh,
no matter what. And then, so I'm between, so you know what I mean? So there's my width, and now I gotta go in the middle of that. You should count 6 rectangles. This one is gonna be different. You're gonna have to calculate it fresh because we're using the middle. So here we go. How do I calculate this area? So 1/2 times, we use what? 0.25, square that. Plus 1/2, and then we use 0.75, square that. Let's continue. 1/2, what's the next number? 1.25, square it. 1/2, what's the next number? Perfect, square it. 1/2 times 2.25, square it, and I think I need one more, right? Plus 1/2 times, and then square that. And then go real carefully. This is not a race. Go real carefully, type that into your calculator. If you're taking statistics, you probably know how to do it really fast. You should get a number between the low and the high. What you guys get? 8.9375. Perfect. Yeah, I think that's it. We'll check our answers in a little bit with the real answer. All right, so let's answer some questions finally. So let's go back to question 1. I need to rewrite this question to make it better. I didn't write it as good as I could have. Use LRAM, MRAM, RRAM. Once you find the distance traveled, what is a particle t equals 3? Okay, so we're gonna answer that question, but I want to know what the actual distance traveled. So on this one, LRAM, this is an under approximation. We got 6.875. RRAM, we got 11.375. This was a over approximation. And then this one, using the middle, we got 8.9375. Do you guys want to approximate what do you think the real value is? Is it pretty close? Yeah, it's 9. Now, hold on, before everyone's like, how do you know? Let me show you. Or I guess okay, let's put a thought in here. If I put more and more rectangles, will my approximation get better? Okay, ready for this right here, guys? Put this idea in your head. All right, if I put an infinite amount of rectangles, LRAM, MRAM, and RRAM, an infinite amount, will all three of them, if I find the area, converge to the same number? Yeah. Now check it out. I put it right here. I'm gonna zoom in. So this, can you guys see that? Is it zoomed in enough? So check it out. With 6 rectangles, it's the same problem that we just did. Did we get 6.875 for LRAM? Did we get 11.375 for RRAM? Did we get 8.9375 for middle? Look with 12, 7.9, 8.9, 10.1. And they did it like this because the RRAM is the rightmost and the LRAM is the leftmost and the M is the middle. Look at with 100. Look at with 1,000 rectangles. Are they all getting pretty close with 1,000 rectangles? What number does it look like? 9. So this particle between t equals 0 and t equals 3 travels 9 units to the right. Does that make sense to you guys? All right, so now let's answer this question. Oh, with calculus, but we're not there yet. I mean, we're in calculus, but we're not. I really don't want to cheat you. No, I'm not going to do it because then that will ruin the surprise when we get there. The middle one on this one would have done like that's the closest one because of MRAM, but you don't want to play that game because sometimes the curve is not always gonna be like this one. You know what I mean? Okay, so here we go. So we know that we traveled 9. So I'm gonna put in here in black. I'm gonna put particle traveled 9 units right from t equals 0 to t equals 3, period. Bless you. So there it is. That's the distance traveled. Now, what else did they want to know? Where is the particle at t equals 3? All right, don't worry. This is a concept that's really heavy, especially for rookies in the beginning. Where was the particle at t equals 0? No, it wasn't at 0. At 5. The velocity was 0 at 0. But the particle was at x equals 5. We're just doing one-dimensional motion. The particle at t equals 0 was at position x equals 5. Does everyone understand? So 3 seconds later passed. I moved how many units to the right? So what is 5 plus 9? So that's where I'm at t equals 3. So I'm going to put, don't worry, I'm going to say it again. At t equals 3, particle is at x equals 14. In case you're confused, this graph, the red curve, only gave me my velocity at a time. It doesn't tell me my position. So think of a curve. Right now we're rookies. We're only doing one-dimensional motion. As you become more and more beast, you will do 2-dimensional and then finally 3-dimensional. So right now you're either moving left or right. At t equals 0, you were at position 5, but the velocity was 0. And then didn't you just tell me between t equals 0 and t equals 3 that I moved 9 units to the right? Well, if I started at x equals 5, I moved 9 units to the right, I'm going to be at x equals 14. Does that make sense, guys? Okay. Don't worry, we're going to go slow. And you're going to see how awesome this is in a little bit because I got a medical question for you guys. Yeah. So that way you guys can see how this is also really good stuff for medical. All right. So here we go. A true false question. And answer it to yourself. Don't say it out loud. So I'm in example 2, true false. It says if F is positive, continuous, increasing from A to B, then LRAM gives an area estimate that is less than the true area under the curve. Justify your answer. So think about it. No, you can write it. You can write it, but just don't say it out loud. Guys, if you're a visual learner, go ahead and create that graph. It says positive continuous increasing. So just draw a random positive continuous increasing function. Okay, here it is. I'm just creating it. Positive continuous increasing. If I have a graph that looks like that and I do LRAM, well, isn't that what we just did right now? Look, this is a positive continuous graph and I did LRAM. And when I did LRAM, did I get area? What did I say? Area under the curve, the exact area or area less than? So what did I get? It was an under approximate. I didn't get the true area. The true area is, I don't want to mess up my pretty graph. Oh, I'm going to mess it up. The true area is all this. That's my true area. And we are going to figure out how to get the exact area. We're just not there yet. We're about 2 days away from that. So we need Friday and then we'll get there on Monday. All right. So true. Let me read it again. Hold on. Gives an area estimate that is less than the true area of the curve. True. That is true. Are we cool? All right. Example 3. Oh, I could say, I would just repeat an LRAM for an increasing function will always be an underestimate. An LRAM for an increasing function will always be an underestimate. So you're saying what if I'm increasing but concave down? That's what you're trying to tell me? I thought you were trying to tell me that. Let's see. Increasing concave down. Check it out. LRAM will still give me under approximate. Oh, well, okay. Then we start talking about displacement. Right now we're rookies. We're just talking about distance. We don't want to get into displacement just yet. I mean, the concept's simple, but it's very easy to confuse it really quick. What's up? Oh, then we can't do area under the curve. It has to be continuous. Obviously, this is tied up to, I don't want to say the word. Okay. It's tied up to derivative. Well, what is tied up to derivatives? What have we been working on that we've been hinting that we're getting it? It starts with an I. Integrals. But hold on, let's not ruin the surprise. Oh, did I ruin it already? Okay. If an MRAM sum, so example 3. I don't know. We're doing Raymond sums, so I think that's like unit 6, I think. Example 3. If an MRAM sum with n equals 4 rectangles of equal width is used to approximate the area enclosed between the x-axis and the graph of y equals 4x minus x squared, the approximation is, and you can use a calculator. There is one with a calculator. Before you use your calculator, guys, from algebra 2, I would really, really like for you to be able to graph that without the assistance of a calculator. I would hope that you would probably go y equals x parentheses 4 minus x, and then you can see that I have a 0 at 0 and a 0 at 4. So then at x equals 2, you're symmetric. So this graph looks something like 0, 4, and it looks something like this. And I hope that you know that from your algebra 2 days. And if you don't, it's okay. I understand that we've been in a pandemic, so maybe you don't have enough practice. But make sure that we're trying to get to that level. Yes.
This is what I was talking about in my science fair, the finding the perfect all this. But you called it hard fair. That kind of.
Yes, I already forgot. Like, I don't even know what I did this morning. Like, so remind me again, bring me all the facts and we'll see what's up. All right, so here we go. What do they want me to do? MRAM? And do they want equal width? Okay, so let's find our delta X. Delta X is, I'm going between 0 and 4, so 4, and I have, am I going too fast? And I have 4 rectangles. So my delta X is gonna be 1. So each rectangle has a delta X of 1. Remember, delta X is just my base. It's just, okay. Yeah. Oh, sorry. All right, so here we go. So here is my, this is 2, so I'm gonna cut it right in the middle, and I'll cut it right in the middle. So, and I'm using MRAM. What's the middle between 0 and 1? 0.5, left, right. There's my first rectangle. What's the middle between 1 and 2? 1.5. Middle between 2 and 3? 2.5. It should be symmetric, so it should be the same, but mine doesn't look the same. Between 3 and 4. Okay. I didn't draw mine perfect. It's all good. It's all good. I didn't draw mine perfect, guys, but it should be symmetric. So I'll label them in a little bit so I can tell you. 1, 19, 20. If I label them, I usually wouldn't, but I'm gonna label them just so I can prove a point here. 1, 2, 3, 4. Those are my 4 rectangles. Rectangle 1 and rectangle 4, man, my drawings are way off. Rectangle 1 and rectangle 4 should be the same area. So you can see that my heights on both of them are off. And then rectangle 2 and rectangle 3 should be the same area. So someone do it one way and someone do it the other way. So let's see, 1, so I'm doing width times height. 1 times, how do I get the height? 4 times, what did I get, 0.5? 0.5 minus 0.5 squared closed. That's my first rectangle. Plus 1, I guess you don't need the 1 there. And then I'm gonna go 4 times 1.5 closed minus 1.5 squared closed. So someone take those two, add them, multiply it by 2. Oh, don't they want the area?
Yes.
I'm just finding the area of each rectangle.
No, but can you explain that word, like how we use the because I don't know the value, but it's really
Where did I get the 1?
like this is crazy.
Area of a rectangle is width times height. The height is dictated by the curve. The curve is 4x minus x squared. So I'm just plugging in an x value into my 4x minus x squared so I can figure out what the y value is.
Okay. Wait, so then you get the one?
I'll show you how to do it fast. The 1 is your delta x, width times height. I'll show you guys how to do it fast in a little bit. So there it is. And what I said multiply that by 2, right? And then someone do it this way. 4 times, don't worry, in a little bit I'll show you how to do it real fast. And then 3.5. Someone do it first 2 times 2, and then someone do it, add them all up and see if it's the same area both times. And I'm in a little bit, I will stop right here so I can show you how to do it fast. Practice with the calculators, guys. Practice with the calculators. First 2, add them up, times 2, and then someone add them all up. See if it's the same answer. What? 11? Is 11 in there? Yeah. Okay, we're gonna find out. You want to learn how to do it really fast? All right. Do you agree that to find the area of that rectangle 1 is just 1 times that y value? And that y value is dictated by this curve right here. So here's how you do it really fast. You go to y equals, and I'm going to type in the curve. What was it? 4x minus x squared. And then I'm just going to do this. There it is on y1. I'm gonna go, because it's 1 times whatever, isn't 1 times whatever just itself? So I'm just gonna go alpha trace y1 at, what was it, MRAM, right? 0.5 plus, remember, this is width times height, but the width is 1. So alpha trace y1 at 1.5 plus alpha trace y1 at 2.5. And then finally, my last one, what is it? Is it 3.5? And this should be that magic number that you guys got. And there it is. That's how you do it, pain-free. But you got to know what you're doing, and you got to know what the calculator is doing. So that's why you got to become one with the calculator. I feel like that's. But if the width was not 1, I would put all that in parentheses times whatever the width is. Because if the width is always the same number, you can factor it out. Does that make sense?
Yes.
Okay. So are we feeling good?
Yes.
All right, can we take some more? All right, so here we go. An LRAM sum with 4 equal subdivisions is used to approximate the end of the sine curve from 0 to pi. Okay, here comes pre-cal. Guys, pre-cal is never gonna go away. You're gonna have it all the time, but it's never even extreme pre-cal, it's just baby pre-cal. Do you know how sine x looks like? Y equals sine x. So here it is, I'm exaggerating it. 0 to pi. It looks kind of symmetrical. I have the high point at pi over 2, because sine of pi over 2 is 1. So here's 1 up here. And what do they want me to use? LRAM? All right, so if I'm cutting it into 4 pieces, so the delta x is the hard part. So let's see, between 0 and pi, let me put pi here. So my delta x is pi divided by 4. The 4 is the number of rectangles, and the pi is because this is between 0 and pi is pi. So we're just gonna go by pi over 4, which makes sense. Pi over 4, pi over 4, there it is. We got all 4 pieces now. My first rectangle, you're using LRAM. So between 0, yeah, they told us to use LRAM. So because they told us to use LRAM, from 0 to pi over 4 is your first rectangle. You have no rectangle. Then the next rectangle is from pi over 4 to pi over 2. Then the next rectangle is from pi over 2 to 3 pi over 4. No? Oh, you're good. You're good. And then finally, the last one is from 3 pi over 4 to pi. There's how it looks. There's a little bit below, there's a little bit above. I'm not sure how close it is to the exact, but they don't want that. They just want to know what the approximation is with this. So here we go. The width of each one is how much of each of those rectangles is pi over 4. So there's my pi over 4 out. So I need, what do I need? My height. Well, I already factored out my pi over 4. The first one was 0, so 0 plus, what is sine of pi over 4? Square root of 2 over 2 plus, what is sine of pi over 2? 1 plus, what is sine of 3 pi over 4? Perfect. There it is. Look for that answer. I think it's letter C. Do you guys see that? How do we feel? Yara, you feel okay?
Yeah, so far I feel good.
Awesome, awesome, awesome. Okay, check it out, guys. Oh. Read that to yourselves for you medical peeps. Read all of that. And then don't worry, it's not even that much. It just takes up the whole page. Yeah. Read it, guys. Read it. It's super awesome. So I didn't go to medical school. I don't know. I think this is what maybe when you go to medical school, you're going to be doing a lot of reading on your own, and I assume a lot of that literature will be something like this. So you can see where calculus is so powerful. Look, guys, look how much we just learned just by reading this. So they inject a dye into the blood system, and then they measure it where do they measure it? At the aorta, the concentration. And then from the concentration, guys, they get this graph here, and they can find, if they find the area under that curve, then they find how much blood has been pumped through how much blood the heart has pumped. Isn't that amazing? Isn't that cool? Like here you can see calculus in action. Like when am I ever going to find area under the curve? Well, here it is. You find the area under this concentration curve, you find how much blood passed through your heart. You guys don't think that's cool? Oh, they explained it right here with the units and everything, milligram, blah, 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 liter of the blood per second. So they just get the concentration, which is, let's see, milligrams per liter. And they do all this analysis with unit analysis, and they get liters of blood per second. Oh, it's the concentration of the dye, not the actual dye. See? It's the concentration of the dye. So they just see the concentration of the dye as it passes through. And then once there's not enough, like once the concentration is very low, they're like, okay, let's calculate. And notice the time in seconds is going really fast. All they need is like a minute, and they can figure out how much blood is being pumped through your heart. Now, are you going to be that doctor that's going to calculate it by hand? No, the machine's going to do it. But if you have an understanding of, if you know like what's going, like, oh, I took calculus. I mean, I'm not saying you need to know calculus to do this question, but what I'm trying to say is school is giving you the tools necessary for you to understand. Someone has to program that machine. Someone has to inject the dye, and then you're the one that's going to have to calibrate the machine to pick up the dye, right? And then you know that you went to med school. You're like, yeah, what it's doing is just finding the concentration of the dye I injected you with. And then from that concentration, I can tell by finding area into this curve how much blood is being pumped. Of course, the machine's doing it, but you have that idea, you have that knowledge of what the machine is doing. You guys don't think that's cool? I think that's super cool, guys. So I just think you should see how powerful calculus is, just not just in mechanics, but in the medical field and anything that deals with motion. Calculus is so strong and so powerful. All right, how do you feel for today? Do you feel like you're good? We still have an activity. You got to practice now. We're just starting finding area under the curves. So we have an activity. You're just finding area under the curves and stuff like that, what we did today. And I want it today, but if it takes you a little longer and you can turn it in tomorrow, that's fine. But let's start it today. Is that cool, guys? All right. All right, Ms. Guetta, I'm going to stop sharing here. Do you feel pretty good?
Yes, I do. And if anything, I can just probably FaceTime with someone in the class if I need help. So yes.
Very awesome. All right, I think I already have the activity uploaded to Canvas, so you can check it out what we're doing. But if we don't, I'll upload it right now.
No, yeah, I've already printed it. I've got it right next to me.
Perfect. Awesome. All right, cool. All right, are you going to be joining us tomorrow, Ms. Guetta?
Yes.
Awesome. We'll see you tomorrow, Miss. I'm going to go ahead and stop sharing it.
All right. Bye, Chav.
Later, Miss.